Steve, let's go.
Can I advance it or you will advance it?
Who's the presenter?
I manage the slides. Tell me when you want to change.
Okay, here we go. Okay, thank you. I'm glad it finally made it. Just a brief background with respect to RISC-V. I initiated and started the group for SV128, and I was very active in the vector group and very active in the privileged instruction group. And I really like Raj's presentation 30, 40 minutes ago. And part of the presentation, his discussion was at the end, talking about the old vector people have gone out and play golf now. Well, I tried to play golf and I was very bad at it. So I went back to say, I'm going to design computers rather than play golf. And we'll see what happens. And I want to thank Matteo and John Davis for inviting me to make this presentation. I'm sorry I couldn't show up. Okay, we're going to go to the next slide. It says presentation outline. There are several parts to this presentation. And before I get to the actual details, I'd like to give some research of what's happened in the past. And then initially I did a full design. And then when I realized I had to be pragmatic, I reduced it. So you're going to see this evolution in the following slides. Now on slide 3. This is a very interesting paper. I would encourage people to read it by Stan Williams of HP. And what it shows is that with Moore's law, we have to be more creative. We can no longer just worry about processor cycle times. And what Stan proposed, now, again, on slide 3, with a pop-up, that we're going from processor-centric computing to memory-driven computing, where we have heterogeneous processors or technology, as you can see in the lower right-hand corner. And we have to figure out how does this all work in an open architecture. And certainly this is consistent with RISC-V objectives. Moving ahead to slide 4. Of the objectives, why 120-bit address space? As I mentioned, you want to have cluster-wide virtual addresses for heterogeneous nodes. And I'll explain momentarily what I mean by time to do something different, not just adding more bits to the address space. But we still have to maintain compatibility, upward compatible with RV32 and 64. I continue. This may sound strange to many people. Otherwise, we will continue to implement and support the sins of our parents and grandparents. Meaning, compatibility, if we continue, we will support things which today we would never do that was done 30 years ago. And the way I first heard this is way back when I was fortunate enough to see Gene Amdow make a presentation, the father of 360, for those who are old enough. And I asked him a question afterwards. I said, in your design for the Amdow machine, I know you support 7040, 7090 emulation. Do you support 1401 emulation, which is a very, very old IBM machine? And he said, sometime we have to stop supporting the sins of our parents, grandparents from a technology perspective. So sometimes we have to break. We can't just continue. So my view is we can design and build, and this is very important, secure and programmable exabyte, zettabyte systems. One last comment on this slide 4. It says the best benchmark is the one your competition cannot run. Roger pointed out that ARM got killed trying to compete against Intel, and he's correct, of course. And one of the reasons is the same benchmark could run on both, and you measured price, performance, and watts, and that wasn't sufficient. But if you go back a little time further, Intel put all its money on Itanium for a 64-bit address space. and AMD could not execute, cannot build an Itanium machine. So they defined their own 64-bit address space for the IA, for the Intel architecture. And that was so successful, they grew, and it was so successful that Intel was forced to basically support the same virtual address space that AMD created. And the reason is you could support big data sets compatible with Intel IA32 that Intel could not do. So that's a very good example of the best benchmark is the one your competition cannot run. And we'll get into this in more detail. Slide 5, some quick background. You can read it yourself, but it shows in the past that when we added more bits to the virtual address space, we simply extended the bits from 16 to 32, 32 to 64. Intel just recently extended for SunnyCo from 48 to 57 because more people had bigger address spaces, etc. Well, what's interesting about that is when they went from 48 to 57, they added 9. Well, you can't add 9 to 57 and get 64. So sooner or later, in my opinion, something will change. And I'm going to make a proposal that is ISA independent, so it supports Stan Williams' notion of a memory-centric design. Okay, let's move to slide 6. Just as a quick background, other people have attempted this. I provide a lot of references at the end of this presentation. IBM did this with Future System. Data General did this with FHP, and I was involved in that project. Intel kind of tried to do it with the 432. So there has been attempts. It just has not been successful. And I maintain many of the reasons why it was not successful is the hardware wasn't sufficient to build machines efficiently at the right price. So going forward, it's time to define 120-bit address space without the need for 120-bit address arithmetic. That is, what is I in A sub I? So I itself is 64 bits, and that maintains the index. And also, again, going back to Stan Williams' chart, we should think of addresses not just what's local in the node, but system-wide, potentially even network-wide, which is something we didn't think about 20, 30 years ago. Now, this was addressed by Christie, actually. He told me he wrote this in the RISC-V spec. You can read it yourself. And maybe, in fact, that's exactly where we are today, debating alternatives about extending the address space. Obviously, I disagree with the conclusion, but it's certainly worth the time to have that debate. And that's where we are today. At least that's where I believe we are today. Okay, and I hope this comes up. I like to use Dilbert every once in a while as my consultant to help me understand things. So the first slide says, Dogbert is chairing the International Data Security Standards Group. The goal of the organization is to make security procedures so inconvenient that they give up hope and you die from bed sores. Let's take pride of being independent from the companies that fund us. I think more and more important, it's always important, but now it's mandatory that security be built into our processors, not after the fact, but as part of the primary design objectives. And we'll get into that in detail. So some other things, and I'm sorry that this is the way it comes across on slide 8. Most people don't realize that, I know you realize it in the audience here, that a virtual address really is referencing the disk, not memory. So it doesn't necessarily just have to reference a disk. That's why it's called the virtual address. That virtual address can reference something else that's virtual. We have network addressing with unique names. Certainly when the communications people went from IPv4 to IPv6, that's what they did. We actually live in a world of unique names. Email addresses, URL addresses, phone numbers. Phone system many years ago globally did this. So no matter where we are in the world, we can use our phone, send messages, etc. So the question is, do we want to have two different address structures, one for the web and one for a processor, which means we have a lot of software to bridge to two domains. And whenever you have a lot of software, it slows things down and it potentially impacts security. So what if a unified name structure could be developed? And this is a question I pose. So now slide 9. The next two slides are interesting because you can see what the bases are of a contemporary security system. And what's interesting about this, and again, I'm not going to read it, this was published in 1971 by Butler Lamson. And it turns out in the 70s, because of Project Mac, there was a lot of work, Project Mac at MIT, a lot of work was done with respect to security in all aspects. Another take on this is, again, the objective of secure systems prevent all unauthorized use of information. A negative kind of requirement, which is somewhat unique. Every access to every object must be checked for authority, etc. And as Dave Clark points out, validity and authenticity is required. And this was in the seminal paper in 1975 by Schroeder-Salzer. So a lot of the basis for what security should be today was done 45 to 50 years ago. It just really a system hasn't been built commercially. Maybe IBM would argue that with System 38, etc., that has all these features. So I'm using this as a basis going forward. Again, previous efforts, IBM built something called FS. That's a reference to it. That's called Raden's H handle. Fabry did something called capability-based addressing. And to some degree, the work, and they're doing a lot of good work in Cambridge with the Sherry project, uses capabilities. And if you have the time and you're interested, I would suggest you get access to these documentations and read it, patents, etc. So the full proposal, and I haven't talked about ISA at all, and that's intentional. Again, going back to Stan Williams' chart, it's 128-bit logical address space. And when I first did this, I realized I was biting off more than is feasible. As an engineer, I realized this is too much for day one. But I had to go through the whole proposal to see what was a rational reduction. And that's, you're going to see a little bit of both now. So a pointer is 128 bits, object ID, byte offset. This would be the full proposal. Object ID is unique. And the definition of unique name is simply a structure that's considered worthy of a distinct name. Nothing more than that. Indexing is 64 bits. Again, ISA independent. If you think about it, our internet system works with routers of multiple companies, but yet we can speak to each other because all the routers deal with IPv4 or IPv6. So my view is, why can't the computer people do the same thing? Object is persistent across time and space. Protection and memory management are independent, etc. So my motivations, and this is now on slide 14, we need better security. We need computer virtual addressing to reflect contemporary uses. We do not want 128-bit flat addressing. So this is where I differ from Christie's comment that I showed previously. I'd like to have pointer interoperability between computer systems. That is, a pointer is a pointer is a pointer. And we kind of have it today that most pointers are byte pointers numbered from right to left. You may not think about that as an advantage, but with IEEE floating point, etc., I can take a database created by a ARM processor and execute it on an Intel machine and vice versa. I think that's a very, very important part of computer architecture these days. Memory centric, etc. So now we go to slide 15, and this is the only slide I have on what a unified name server would be. This would be equivalent to, in essence, what a DNS is for web servers. This is very controversial, and I honestly doubt this will ever happen, but I had to go through this exercise to understand what a reduced system should be. So what does protection mean? You have ACLs, access control lists, matrix, protection domains, and you have to have a way of revocation that when someone is no longer, an application is no longer, should have access to data, you have to have a way of saying revoke it. So just simply, conceptually, what an access control matrix is three-dimensional, current domain, target, source, and you have a whole bunch of things called permissions, object lengths, etc. And I'll explain what that means later. Authentication, again, you can read it. And the point is we have to have an access control list. In essence, we have an access control list now, but each company has their own access control list. So if I'm accessing Adobe, Adobe has an access control list for me, for SteveWallach, and for everyone else who is licensed Adobe. And Microsoft has their own. So in essence, we already have a 3D global distributed access control list. It's just not globally referenceable. A typical access, this is now slide 20, ACL entry. You have to have sub-objects, and I'll explain what that means later. You have to have mediated access. And you have to have the ability for an application to restrict its environment of execution. Not just the operating system, but the user itself may want to restrict how a certain application has access to its data. You have to have a protected domain. A domain is simply a set of access bits for that domain. They are, repeat, not hierarchical, unlike rings. It's simply number of bits saying for this domain what you do. And I'll begin explaining how I handle viruses, malware, etc. Again, it's the principle of least privilege. Revocation, this is always a controversial, this is slide 22. You have to have a way of killing things. So the name server, whoever owns that object simply says who does or does not have access to the object. If you have a capability, it's a little bit different because if you have the capability, theoretically, you have access to the object. And I'm not going to go into this in detail, but for those who are interested, the original paper by Fabry and the recent papers by Watson, etc., in Sherry, which talk about how they handle revocation. So now let's see what we really want to do. Now, what I mean really want to do is this is something that with the right team, I can start going into a development project within months. So this is now the pragmatic part of the presentation. And I thank my parents and grandparents for helping me, and let's get down to reality. I want a second chance. So here's what I propose, and this is in GitHub. There's a full spec that I submitted to GitHub. So if you can get a GitHub, you can find this in its gory detail. It's 4 domains that are non-hierarchical. I'll explain what I mean by a personal domain for sandboxing. We really only interpret a 96-bit address with a 32-bit object and a 64-bit object offset. We're upward compatible with RV32 and 64, and we have logical to physical translation using RV64. For those who may say, how do you do compatibility and all this, I'll show you. And just to set something straight, 40 years ago, I did this at Data General. I had upward compatibility from 16 bits to 32 bits. It doesn't make a difference as long as you understand how to do it. In the right side of this, you'll see several pop-ups. This came right from the RISC-V spec, the privilege levels, as you can see. They show 3 privilege levels that are hierarchical in nature, and they show what part of the operating system hypervisor use these levels. This is how the PMN using hypervisors using an Intel diagram would run on this. When I mentioned this to, it's irrelevant who I mentioned it to, I said, why are we copying what Intel did? And the reply back is, so it's easier to port Linux. Now, is that good or bad? I'll let you decide whether that's relevant. But if we're developing new technology that's taking us in decades, why should we carry forward something that was basically designed 20 years ago and modified piecemeal rather than a general approach from day one? That's my opinion. Obviously, you can have your own opinion. That was on slide 24. So continue on slide 24. I've taken that previous diagram and said, okay, we now have 4 domains. One for the hypervisor, one for the guest OS, one unused, and one user, as opposed to the previous diagram. And each domain can have its own personal domain or shadow stack. So if I take some application, I can restrict it in my address space of what it can access. I think that's an important part of any new design. Slide 25. As you've seen, I've taken this to the level of actually defining what bits mean. My goal is to support PCAS, that is system-wide virtual addresses, which a lot of people are using with languages like UPC. The various bits of the object type can say what the offset is, and I'll explain what I mean, why I have a byte offset of RV64 and RV32. So it puts some semantics in the address, which even today in 64-bit Intel, when it was only 48 bits, many operating systems used a higher order 16 bits to define certain things. It was convenient to do it. But, since it wasn't part of the architecture, when Intel expanded it, the use of those bits may disappear. So this is have a full interpretation of what those bits can mean. Here's an example of what I mean by RV64 into RV28. A 64-bit address for user running RV64 binaries. When it generates a virtual address, the hypervisor or guest OS simply appends a higher order object with the number 4. So the address space is in 64-bit address space is embedded in 128 or 96-bit address space. The same would be true for the 32-bit address space embedded in the 96-bit address space. So when you get to the operating system, it doesn't really care whether it was RV32, RV64, or RV or SV128. This is an example of a page table, which I can't tell you how long it took me to create this diagram of how to map a 48-bit address space because of the small page size into a physical address space. But now what you would do is hash it. This is not IBM uses hashed addresses for several of its machines when the addresses get big. But what happens now is the object ID on a per domain basis is, is hashed. First, there's a bounds check. Then the contents of an entry is various control bits, physical address of the first level page table, a bounds check of the virtual address, and a system-wide unique virtual address, which can be used in the TLB without having to flush. This is the benefits of this approach. It turns out bounds checking is very, very important for operating systems and for security and reliability. And each domain has its own table. And the unique TLB naming, I realize many people may not understand this, but when you only have a process-oriented address space, you have to flush the TLB between context switches because the address is not unique. If it's unique, you don't have to flush it, which means you have more performance. You may have gathered I'm very, very interested in server performance for many users. Slide 27. The bits, these various configuration bits, is the classical read, write, execute per domain. Also, you have the ability to add a personal domain or personal access bits for, an object. So if you bring in a helper application, there's a way of restricting it to what it can do, and I'll show you now. Domain switching is very classical. You have a domain call instruction, bounds check, entries. And one of the things you do is stack saving and switching. Now, I'm sure some of you who are Linux gurus are going, oh, we do this in software now. You don't need the hardware to do this. That may be true, but it's a lot faster doing it this way. And also, there's all this concern now about Spectre, Meltdown. A lot of papers been written in the last year. By having this approach, you can have validate instructions that if I'm passed a pointer from a user, I can validate whether the user, make sure that user is not trying to reference an OS data or a hypervisor data. And I've been told by some of my Unix guru friends that there's an elaborate procedure in the Unix kernel to validate pointers. And if you know what you're doing, you can put it in hardware. Okay, compatibility with RB64. You can see what Dilbert thinks about this. Our only long-term hope for survival is to innovate in the ways that cannibalize our current products. And in essence, that's what the computer industry has been in the last 30, 40 years. So yes, we can execute an RV, A.out, etc. This is the way you do it. And if you do it this way, even in a 120-bit address space, you can still use all the 64-bit utilities because one address space is a subset of another. This is what a shadow stack personal domain is. This addresses things like heap feng shui attacks, heap overflow. A lot of software like Apple does this is randomize return points and entry points. You can eliminate all that if you have the right set of hardware to create your own stack and force and you return things via the caller stack, not the callee stack. That's the fundamental difference. Here's a pictorial of that where, again, it's hardware maintained, and you could put this on any machine. You don't need an RV or SV128 machine. Again, what I'm trying to do, you may have gathered, is all these things that come up, and we'll get this in more detail. It's not just the address space, but we have to design secure machines. So it's not just the best benchmark is the one your competition can't run. We're getting to the point is the difference between someone buying architecture 1 versus architecture 2 is the security aspects. A week doesn't go by where you read about some security feature hole in hardware or software, whatever. Now, I'm not trying to say I will solve them all, please, but I may solve enough of them that someone may say, I'm not going to attack that one. It's too hard. I'm going to try another one. Maybe. I could be totally wrong. The benefit characteristic of all this is the Google analysis on the Android kernel that 44% of all kernel bugs are incorrect balance check. That's a lot to eliminate 44% of kernel bugs. You can see I mentioned the system-wide. I now have Stan Williams' chart on slide 32. Direct support of PCAS-like addressing. So if I can build a system with thousands or tens of thousands of node with a system-wide virtual address, and with a common pointer, the processes are not homogeneous, they're heterogeneous. So I don't force anything. I can have specialized processors for AI or machine learning or for whatever. And at least the people I speak to or speak to me, that's where the world's going, if not already. And it doesn't preclude anything else. And just lastly, part 4, secure design. Some people, the younger people, may not know what that chart is. Way back when I designed hardware, that's the template I used to draw gates. It dates me, but that's what we used. Believe it or not, there was no Verilog, etc., no graphics. And part of the fundamental approach to microstate is there was a lot of work done by the Kaiser proposal, European University. That was a very, very good proposal. We need formal method compilers. A lot of work is being done on that. And when we have speculative state, like previous presentations, I heard all about out of order execution, et cetera, we have to view that state as speculative where appropriate and not part of the operational state. So therefore, we have to be careful when a branch is taken, whatever, we flush that state and it's not maintained so someone else can come along who's evil. And this is something I believe that n minus k secure cores is better than n unsecure cores. So a common question is, does it make a difference whether I have 32 cores on a die or 28 secure cores or 26 secure cores? Most people I speak to, when I was just recently at SC19, say, oh no, I'd rather have 26 secure than 32 unsecure, because who knows, maybe marginal return for the performance on 32 cores. It's something to think about. The summary compared to Sherry, there's a good summary of single address space operating systems. You can see the reference. And hopefully at some point, we're building a prototype with FPGA and or software. And I end it with Dilbert again. This PowerPoint slide could change our entire company strategy. The rest of the industry will have to copy us. That could change the entire world. Someone has been having delusions of effectiveness. Thank you. So hopefully you're able to follow it, and please feel free to ask any question you'd like.
Can you hear me? No.
I can barely hear you. Go ahead.
Okay.
It's garbled.
Ha dicho que sí, ¿no? Que no. Yo tampoco.
Can you hear me, Steve?
Yes.
To me, yes. To you is no.
And not for me. No. Okay. It doesn't work. Okay, anyway, if there is any question, we can try to do it from here. No, can you hear me now?
I can hear you now.
Okay. I will ask attendants to come to the microphone if they want to put you a question.
I think that's a good idea. Thank you.
Then, if there is any question, you can, you can just come here and address the question to, no?
Yes,
Please,
please.
Frank, go for it.
Hi, Steve. Can you hear me?
I can hear you.
Yeah, it looks like the room is full. Nobody dares to ask a question. This was an outstanding presentation. So let me go back to your security part. I think most, if not all, of the attendees remember this famous Spectre and the meltdown attack against the Intel processors. So,
Correct.
would the proposal you have made, let's say, implemented the right way, would that have made such an attack impossible?
Yes. Basically, it's a combination of validate pointers, meltdown, and Spectre is, there are various solutions to Spectre. One of the things, and I have a whole separate presentation on that, is where I create separate state, speculative state, for branch target buffers, reorder buffers, etc., that rather than speculating and changing the state of the current buffer, I have separate buffers. Other people have said this also. I'm not claiming this is unique. So when you're doing things like cache coherency and other things, you're not referencing the data in the normal operational cache. And by doing that, again, it adds complexity to the cache or buffers or everything else. But you eliminate a lot of these issues. And that's why one of the slides I talked about having unique state for security, that it's a mindset of design. When people do hardware design, that they think of, the spec is to do this in 3 cycles with so many gates. Having done this myself, I have to admit it. But you also then now have to have new objectives of, if you create other aspects of performance like additional buffers. We heard people talk about memory order buffers, etc. That when those buffers are not used, you have to flush them. You can't leave state hanging around. You can't have stale data. And that's where a lot of security attacks occur. I mean, I can go with each one in detail, but in essence, it's you have to understand what the attack could be, how to prevent it, and how that's reflected in the hardware. Now, I know in Intel's case, I found out afterwards, they actually changed the microcode on a lot of the chips to eliminate this, but it slowed some things down. At least that's what I was told.
Okay, you know, this was a complex answer to probably a hard question. So I'm standing here in front of the audience, and I remember we had a discussion on that attack, and I think what came across quite well is that your implementation would significantly increase the, let's say, I don't want to say stability, but the security of systems, right?
Correct.
So back to the audience. Okay, so then I throw in a final question. You mentioned vector computing initially, right? And
yes.
The European Union is supporting, financing an initiative we all know, and here in Barcelona, a lot of effort are being put into developing a vector processor. So. Based on RISC-V, so could you just quickly comment on vector computing on RISC-V. What's your take on it, current status, and is there anything we could do even better in future?
Okay, well, thank you. That's a good question. As I said, I was active in the vector computing working group, and having built 5 or 6 vector computers, my comments were based on experience, not just based on experience. And from what when I last saw it several months ago, I was very encouraged. And it's vector registers, there's lots of them, they're configurable, et cetera, et cetera. But there are 2 other aspects of vector computing. One is to get real performance in vector computing, you have to have a memory system that can support it. If all the vectors that you reference from memory with the load vector instruction come from a cache, I think you will be disappointed with the level of performance. So this is an implementation detail, not an architectural detail. Most server class vector machines have caches for scalar, but go directly to memory for vectors. That's true of the Japanese, true of Cray, true of Convex. Way back when IBM and DEC built vector computers, which all the data came from the cache, I remember Jack Dongera used to have charts to show when the data set exceeded the size of the cache, performance dropped by factors of 10. That's one thing. Whoops. The next thing is software. It was mentioned that Randy Allen is now an employee of Sci-Fi. Allen and I know each other since 1980, or actually 82, because he was one of Ken Kennedy's best grad students. And the Convex compilers actually implemented a lot of his dissertation. And over the years, we've stayed in touch. You have now one of the top vector compiler people in the world employed by Sci-Fi. And I hope that Randy and his team, because it's not just one person, is given the opportunity to produce a world-class vectorizing compiler using the LLVM technology. In my experience, it's nominally a 2-year project with the right team to beta test. And I hope, I don't know Sci-Fi's plan, but I hope that happens. And if vector computing with that level of software, I think you'll have an extremely, extremely competitive vector system.
Okay, Steve, as Frank said, thank you very much for this outstanding presentation that, frankly speaking, I cannot follow you too much because I'm not specialized on this domain, but probably people in the audience appreciate a lot your talk.
Okay, if someone wants to send me an email, by the way, steve.wallach@gmail.com, feel free. Okay, thank you very much for that. Sorry for the technical problems. Tomorrow we will still be here with several presentations in the morning. You have the agenda, and yes, I do.
Hopefully if we can transmit by streaming, you will be welcome to attend. Okay?
I appreciate that. Thank you.
Thank you very much for your presentation. Okay, thank you and bye-bye. Difficult, that, yeah?
Well done.
Thank you.
Okay, then now that's finished. It's time to go back to home, back to the hotel. The people that will attend the dinner, we will try to be there around 8 or 8:15 the maximum. and then we will have the dinner there. Tomorrow tomorrow it will be still more difficult than today. We will have here also the meeting for the other network, the Kappa H network. Early in the morning at 9, they will start in this room. We will start in Q9 1009, I think. Yeah. And then we will meet all together at 10 o'clock for the coffee break. And after that, I will ask both networks to, let me say, senior people like myself to attend the common sessions in this room, and other people will attend the common sessions by streaming in Q9 1009. No, sorry, Q4. Okay, this is in the agenda. I'm really tired, okay? And that's all. It was announced, or was in the agenda, was also a meeting for the network now. This is not necessary. We will try to meet tomorrow afternoon, the Red RISCV network, and right now, see you later on in the dinner, or see you tomorrow in this room. Thank you very much.
Gracias.